In number one, we are putting these compounds in order of increasing heat of hydrogenation. So recognize that the main thing we're talking about here is conjugation. Conjugation is the idea that you have double bond, single bond, double bond, and they're alternating. So conjugation really increases the stability of a molecule, and that's kind of the point that they're trying to make with these slides. How do they measure that? With the heat of hydrogenation. The heat of hydrogenation is kind of the idea that they are measuring if we were to take this double bond and add hydrogens right here so that the double bond goes away and becomes a single bond, how much energy did that process produce? And they measure that. And then from that, they're able to just determine the stability. Okay, so in letter A, the first thing I've done is, and letter A is down here. The first thing that I've done is drawn all of the possible structures that we're trying to analyze, and then I went in and I counted the number of pi bonds, how many double bonds were present. This, let's get my laser pointer back. This one had 2. This one's got 3. The rest of them all have 2 pi bonds. So I counted the number of double bonds present. This one, the one that has 3 pi bonds, is going to have the highest heat of hydrogenation, even though those bonds are conjugated. And I've highlighted in yellow all the conjugated bonds. So even though these are conjugated, the fact that there's another double bond to remove, that process requires more energy. Okay, so, or involves more energy. So this one is going to be my number 6. It has the highest heat of hydrogenation because there are more double bonds. The rest of them, so now we're going to talk about the rest of them that all have 2 pi bonds. Okay? Let's start with the ones that are not conjugated. The ones that are not conjugated are going to be the ones that are least stable. They're going to have higher heats of hydrogenation. Okay, so this one and these two are going to be my numbers 3, 4, and 5. So how did I put those in order? Well, this one had double bond right next to double bond. That's a high energy situation. Okay, so that one is my number 5. And then come over, these two are going to be my number 3 and 4. So how did I tell them apart? Neither of them are conjugated. They both have 2 double bonds. The last thing you want to look at is how substituted the double bonds are. So for example, this double bond right here is mono-substituted because there's one thing coming off of one side of it. There's one group coming off right there, and that is the only group. Everything else around it's a hydrogen. This double bond is disubstituted. There's 2 groups coming off of that double bond. This one is mono, and this one is mono. Well, your substitution, when you start adding groups to your double bond, that actually increases your stability. So the fact that this one here has a disubstituted group and the other one did not makes this one lower in energy. That one ended up being my number 3, and then this one was my number 4. Which brings us to the remaining ones. These are the remaining 2 that we need to talk about. They both have 2 pi bonds, and the 2 pi bonds are conjugated. It's double bond, single bond, double bond. So then what we need to look at is substitution. This double bond is mono-substituted. This one is di-substituted. This one is di. This one is di. It has 2 groups coming off of the double bond. So this one over here that I've chosen to be my number 1, it has 2 double bonds. They are conjugated, and both of them are disubstituted. So that one was my lowest energy situation. We're going to apply the same concepts to letter B. Letter B is up here. The structures are all drawn for us. Okay, I'm going to count total bonds first. This one has 3 total bonds, 2 total bonds, 2 total bonds, 2 total bonds, and 2 total bonds. That right away makes this one over here my number 5. Okay, so that one's my highest heat of hydrogenation. The rest of these all have 2 double bonds. So then I'm going to look for conjugation, and I've highlighted the conjugation. So let's talk about the non-conjugated ones first. Okay, these 2. They both have 2 bonds. They both are non-conjugated. This double bond is disubstituted. It has a group here and a group here. This one's disubstituted. This one is trisubstituted. It has a group here, and a group here. This one is disubstituted. So I have made this one over here, number 4, and this one, number 3, number 3 got some more stability from the fact that one of the bonds was more substituted. That leaves us with this one and this one. They both have 2 bonds. The bonds are conjugated. So the next thing we need to look at is substitution. This double bond is tri-substituted. This one's di-substituted, di-substituted, di-substituted. This tri-substituted double bond right there made that my lowest heat of hydrogenation. That one was my most stable structure. And then the other one is my number 2. Number 4, we are given some allylic carbocations. So they are allylic because you have a double bond, and then 1 over from that is the position where the carbocation is located. So they are allylic carbocations. Anytime you have allylic carbocations, you have resonance. Keep in mind that a double bond is made up of a pair of pi electrons. They have a negative charge. They're going to move towards the positive charge. So you want to have one arrow. It should be a double-sided arrow because 2 electrons are moving, and it's going to move towards the positive charge. When that happens, the positive charge moves to where the electrons left from. The electrons moved towards the charge, and now the positive charge is in a new location. For the question also asks us to identify which one would be the more important resonance structure, and that has to do with the stability of your carbocation. This one is a primary carbocation because the carbon that it is on is only touching one other carbon, whereas this one was a secondary carbocation. This one is the more stable carbocation. Same thing happened in the next question. Your electrons moved to here, which moved your positive charge to there. So this carbocation is primary. This one that was produced over here is tertiary. Tertiary is a more stable carbocation. And then in the last example, the electrons moved to here to give you a double bond in that new location, and that moved the carbocation to there. So that gives us this new structure. They are equally stable. In both cases, the carbocations are secondary. Here at number 5, you've got 3-bromo-1-methyl cyclohexene, which looks like this, is undergoing solvolysis in hot ethanol. 2 products are formed, and it asks us to propose a mechanism that accounts for both of these products. I do want to point out this is an SN1 mechanism. With an SN1 mechanism, you have a good leaving group. In this case, it's the bromine, and like in this first step here, what you see is the good leaving group leaves. That leaves a carbocation behind. A carbocation in an SN1 mechanism, since you do produce a carbocation, you do have a chance for a rearrangement to take place, or in this case, resonance is happening. So my original carbocation looked like this. It has a resonance structure where those electrons move to here and give you another carbocation. So the positive charge is here and here because of resonance. And then here is the leaving group that just left. It's just hanging out in the solution now. Your SN1 reaction typically reacts with the solvent. So the solvent is ethanol. That ethanol has a pair of electrons that are going to reach out, and it's going to add at those carbocations. So over here in this next step, you can see that I've added in the location of the 2 carbocations, I've added the ethanol. Keep in mind with the SN1 reaction, if you have a neutral solvent, you're going to end up with a group here that has a positive charge because you added it to a location with the positive charge. So it still has the positive charge, but now it's on the oxygen. So I've produced 2 products, produced this one right here and this one right here by adding the ethanol to the 2 places where the carbocation was located. Then another step involves another molecule of ethanol comes in, takes away these 2 hydrogens to give me my neutral products. Okay, so this was an SN1 reaction. The carbocation rearranged, or it didn't rearrange, but it went through resonance to give you 2 positions where the ethanol could add. Here in number 7, we are proposing a mechanism for these reactions. We're going to do A on this slide and C on the next slide. So what I have first written is the overall reaction. They tell me right up here, 3-methylbutene-2-ol is going to react with HBr to produce 1-bromo-3-methylbutene-2-ene and 3-bromo-3-methylbutene-1-ene. So first of all, I drew what was happening. And you can see the two places where that bromine is going to add. And then we want to use mechanisms to try to explain why it added in two places. This is an SN1 reaction, so we need a good leaving group. The good leaving group is going to leave us behind a carbocation. The carbocation may move around due to either resonance or rearrangements. And then a nucleophile is going to add at the position of the carbocation. So that's kind of overall what's about to happen. Alcohol by itself, not a good leaving group. So the first thing that happens, this is being run in acidic conditions, HBr is an acid, so the alcohol reaches out and it grabs a hydrogen from the HBr. Now you have a protonated alcohol. The oxygen now has two hydrogens and a positive charge. That can leave as water. Okay, so we made a good leaving group by protonating the alcohol. A good leaving group leaves and leaves behind its positive charge. So the positive charge is originally right there. That positive charge goes through resonance. So the electrons, that is an allylic carbocation, which means resonance can happen. So the electrons that are part of the neighboring pi bond move towards it to give me another carbocation as well. So the rest of this reaction is going to happen in two places. It's because we've got two potential carbocations. The rest of the reaction involves this bromide ion that was produced way back in the first step. Over here, the remaining bromide ion then comes in and adds itself to the two places where the carbocation is located. Now that is with an SN1 reaction in the previous example, we had a neutral solvent and it added and gave us a positive charge. In this case, I've got something with a negative charge adding to the carbocation. I end up with a neutral charge. You've got a positive and a negative coming together. That's going to give us a neutral charge. So that explains how we got two products. It added at the location of both of the carbocations. So what you're looking for in these problems, you're looking for your leaving group to leave. When it does, it leaves behind a carbocation. You want to see if you can move your carbocation at all, and then that will show you the locations where you're going to be adding something to the molecule. This is letter C of problem 15-7. Once again, this is going to be an SN1 reaction. Overall, we've got cyclopenta-1,3-diene plus bromine forms 3,4-dibromo-cyclopenta-1-ene and 3,5-dibromo-cyclopentyl-1-ene. Okay, so we're ending up with 1,2 and 1,4 addition, which we just saw in the notes in this section. And what I mean by that, the bromines have added 1,2 and 1,4. That is very common when you have a diene like this. Okay, the diene that's conjugated like that. In terms of a mechanism, your electrons that are part of your diene, this is a pair of electrons that can reach out and grab something. So that's what they did. They reached out and they grabbed this bromine right here. Now, this whole section is about allylic carbocations. So that's the goal here. We're trying to produce an allylic carbocation. That means I want my carbocation to be here and my bromine to add here. So that's what I've got over here. I've got my carbocation and my bromine in place. That now I have an allylic carbocation, so it's going to go through resonance, which leaves me with two places where my carbocation can be located. At that point, the bromide ion that was produced way back here in that first step, that bromide ion comes in and it adds at those two locations of the carbocation. So that's how we ended up with 1,2 bromide addition and 1,4 bromide addition, which is a very common addition pattern when you start with a diene. Here in number 9, when methylene cyclohexane is treated with low concentrations of bromine under irradiation by a sun lamp, 2 substitution products are formed. So this is going back to a radical reaction. The sun lamp is providing the heat and the light that is needed for this initiation step. Recall that in a radical reaction, you're going to have an initiation step, propagation steps, and then typically a termination step. The initiation step is creating that first radical. So the sun lamp is causing this bond to break homolytically, meaning one electron goes this way and one goes this way. So you have produced 2 bromine radicals. So the initiation steps produce your radicals. Propagation steps use a radical and then produce a new radical. So propagation steps can keep happening over and over and over again. You use a radical and you produce a radical in a propagation step. Now, this reaction, the key to this is that an allylic radical is much more stable because it can be resonance stabilized. So here is my double bond. 1 over from that is the allylic position. So that's where my radical is going to form. Always recognize that if possible, you're going to get an allylic radical. Okay, so here's how that formed. You had a hydrogen hanging off here. There's a bond between that carbon and that hydrogen. One of the electrons from that bond came here, and the electron from the bromine radical came together. We just formed a bond right there between those two. The other electron from this bond went on to here. So we have formed HBr. There's now a bond between HBr, and there is a radical right here in the allylic position. The allylic radical is resonance stabilized, so you do need 3 arrows to indicate resonance for a radical. To move that radical, and recognize that they're going to be half arrows because each arrow is representing one electron moving. So the radical moves to here. From the double bond, one of those electrons moved to here, and one moved out to here. So we have shifted the double bond to here. Do you see how 2 electrons have come together? We've shifted the double bond to here, and we've shifted the radical to here. So the double bond is going to, that is 2 electrons. One goes this way, one goes this way. That moves the double bond to here and the radical to here. Okay, so that's how we got this resonance position. We've got 2 places where the radical is located. That is the 2 places where your bromine is going to come in and add. So in the next propagation step, we've got these radicals. I'm going to show the mechanism for this one, but it happens on both of them. The radical is 1 electron. Now notice we're adding that back to one of those original bromine molecules, not to the bromine radical, but to one of the original bromine molecules. This bond is going to break. 1 electron comes here and meets with the 1 electron from the radical. That forms a bond right there. Another electron comes onto here to form another bromine radical. So it's a propagation step. It used a radical and produced a radical. So overall, the 2 locations where these radicals were located is where bromine added to give you your 2 products. Number 11, we are predicting the products of light-initiated reactions. So that leads me to believe that we're going to be doing some radical reactions. We're starting with NBS. NBS is just something that you add when you want to add bromine in low concentrations. So by adding NBS, you're producing bromine in low concentrations. The solvent is carbon tetrachloride. The following starting materials. Okay, to begin with, cyclopentene. So here's my starting material. I have all my starting materials in blue. Then I have the radicals that are produced in green. And then I have my final product over here in purple. That's kind of how this thing is organized. What you need to recognize is we're going to be producing allylic radicals. So here is my double bond. The radical is going to be in that position right there. So there's my first radical. And then I used 3 arrows to show you the resonance for that radical. The double bond splits. 1 electron goes this way and 1 goes that way to produce the new radical. And the other electron from the original radical moves this way to put the double bond here. So the double bond has moved to here, giving you the radical now there. So there are two positions where the radical can end up, which gives it a lot of stability. However, these are still the exact same molecule. So for this one, we only end up with one product. The bromine is going to come in and add at the location of the radical. So you're going to be adding that bromine in the allylic position. For the second one, 2,3-dimethylbutene looks like this. You want to put the radical at the allylic position. So that's one of these positions out here. Could have been any of them. Okay, it's very symmetric. So I put it here. That is going to be moved through resonance. So the double bond moves to here, putting the new radical right there. So there's two places where the bromine can add. If it adds here, then your final structure looks like that. And if it adds here, your final structure looks like that. So you get, overall, you get two products. For this one, okay, so you've got an aromatic situation there. You've got benzene. This is actually toluene because it has the methyl group hanging off. Okay, so it's going to produce an allylic radical. That's going to be here. Okay, so that's the only place that that radical can go. Now, really, you're not going to get any more resonance structures out of this one, because in order to do that, you'd have to move one of these bonds out of a benzene ring. Benzene is incredibly stable. In the next chapter, we're going to be talking about aromaticity and how this aromatic structure here is so stable, and it's not going to give that up by moving a pair of electrons. Okay, so there's really only one structure for this one, just because it's a special case that involves benzene. That is where your bromine is going to add. Number 14 is using the Diels-Alder reaction. Recognize that with the Diels-Alder reaction, you're always going to have a diene and then another alkene. So a diene and this is typically called an electron poor dienophile. The reason it's electron poor is very often it has something over here that's pulling electrons, so it pulls electrons away from it. And it's a dienophile because this diene likes it. So this is an electron-rich diene because it has these two extra pairs of pi electrons, and then an electron-poor dienophile. So that's kind of the terminology about these two structures. I've drawn in the arrows for what's going to happen. This is a conjugated reaction, which means everything happens in one step. These electrons move to here, so you end up with a double bond right there. You can see my product has a double bond right there. These electrons move to here. They form a bond between these two spaces right here. That's how that bond right there was formed. These electrons move to here, forming a bond right there, which is how that bond ended up. So overall, you are producing, for all of these, you're going to produce a cyclohexene. So here's my cyclohexene. Whatever was attached to this bond remains right there. So it still is in place right there. In terms of like where things are, here is my alkene. That is that bond right there. A lot of you also found it helpful to see this numbered. This is carbon 1, 2, 3, 4, 5, 6. Over here, that would be 1, 2, 3, 4, 5, 6. So that is not the official numbering if you're trying to name it. That's just trying to label carbons so you can see where everything ended up. Okay, let's take a look at letter B. Letter B is very similar. Okay, so the only difference is I have some stuff hanging off. I have that hanging off over there and that hanging off over there. But this stuff that, let's highlight it. This stuff right here is going to form a hexane. It's actually going to be a cyclohexene because you end up with a double bond right over here. Okay, so there is where my cyclohexene is. You can see that my double bond ended up right there. Hanging off of this carbon, I have this methyl group. Okay, and then hanging off of this bond right here, I still have the same stuff hanging off over on the right-hand side. So like there is that bond. If we were to go in and number it just so you can follow along with the carbons, if I call that one 1, 2, 3, 4, 5, 6, then this is 1, 2, 3, 4, 5, 6. Okay, let's look at letter C. In letter C, When your diene is part of a ring, then you're going to end up with a fused structure. So my product, still the major part of it is a cyclohexene, but when it's fused, you're better off to draw it like this. That just fixes your bond angles a little bit. Now, these two carbons right here are kind of extra. They are not part of the cyclohexene that I'm going to create. I mean, they're still hanging off of it, but they're not the major part. So those two end up here as kind of a bridge. So I've drawn two extra carbons in up there. And then these two right here are these two right here. Recognize that when you go in and draw the arrows, like this one comes to here, this one comes to here, and this one comes to here. This last movement that I just drew, this arrow right here, that is 2 electrons moving. So that's one of those pi bonds. This thing started out with 3 bonds right there. It's going to drop down to 2. So that's why in my final structure I had 2 bonds right there. And then hanging off of those carbons, I've got whatever is hanging off of those carbons. The only thing I did leave off is this arrow right here has moved the double bond to right here. Okay, so that one was a little bit different because we were starting with a cyclic diene. Okay. Letter D is another cyclic diene. So my diene is part of a ring. That means I'm going to start with my cyclohexene looking more like this. Okay. The part that's it's got one extra carbon, so my cyclohexene is going to have 1 carbon in its bridge. In terms of my arrows, this one's coming to here, this one's coming out to here, this one's coming to here. Okay, so I ended up with a double bond right there. Whatever was hanging off of those 2 carbons is still hanging off of these 2 positions. And that's kind of my thought process. And then like however many bonds you had right here gets reduced by 1 when it's drawn right there. Number 15 has us working the Diels order in reverse. So we're given a cyclohexene and we're trying to figure out what they started with. So in my cyclohexene, wherever your double bond is, that is where your diene was. Like here is my original diene. Okay, so that is that product right there. And then this would have been where my alkene was. Remember that this bond right here drops by 1. Like it's a single bond here, that means it needs to be a double bond over here. Okay, and then whatever's hanging off of that one is still hanging off of it. So that is how I predicted what I was going to end up with. We can number some things. This is what I ended up with in my cyclohexene, and that, once again, that's not the official numbering for that structure. Just out of habit, I'm numbering starting at the top of the diene. Okay? But it's not, if I were going to name it, I would need to number that differently. Okay. Let's do the same thing for this bottom one. Okay, so I found my double bond right there. Okay, this is going to be my diene. Okay, and then so my diene looks like this right here. It still has those oxygens and those methyl groups hanging off. And these right here, those are methyl groups. That is not a negative sign. That's that methyl group right there. Okay, now I also see that I ended up with a double bond right there. That means that I started with a triple bond right here because that's going to drop by 1. So I had a triple bond, and then whatever was hanging off of that triple bond is still hanging off of it. Okay, let's look at letter B. In letter B, here is my alkene. So that's where my diene is. I see that I've got a bridge here. That part that I have highlighted is my diene. You can count the carbons. You can see that it should be a 5-membered ring with an oxygen. So that's how I got this. That I have highlighted is how I got my diene. This is the bond that is part of my alkene, which is right there, and it has a cyano group hanging off of it. Letter D is very similar. What I have highlighted there, over here, that is my diene. And you can see that it's got the traditional diene plus 2 extra carbons. So that needs to start as a cyclohexyl diene. Okay. And then I also see that this bond right here is which would be where my alkene would come from, my other structure. Since that's a double bond, in my original structure it needs to be a triple bond. And then whatever's hanging off of it continues to hang off of it. Okay. In letter E, here is my diene. So you can see how I've drawn that right there. And then this group right here is my alkene, and that needs 2 cyano groups hanging off of each carbon. Letter F, once again, I have highlighted. When I see a bridge structure, you want to find your diene. This double bond is in the center of your diene. That's that double bond right there, that bond right there. Okay, so my diene has this extra carbon right here, which is that carbon right there. Okay, and then this bond right here is that bond right there. Okay, and whatever's hanging off of it continues to hang off of it. For 16, we are predicting the major product for each of the Diels-Alder reactions and including stereochemistry where appropriate. So for letter A, I do notice that my diene is a ring. So that means I needed to start with the cyclohexane that's in kind of the position where this is coming up so that I can get that ring. And then it's got this extra carbon here, which is my bridged carbon that I have in place right here. Okay, and then there's no stereochemistry issues going on with my diene. Then I look over here at the alkene. The alkene, I don't see any stereochemistry issues there because this group, if it was cis to a hydrogen and trans to a hydrogen, so there's really no stereochemistry to consider there. This bond right here is this bond right here, and it has the CN group hanging off of it. So that one was pretty normal. In letter B, this is my diene, so that has a CH3 here and a methoxy group here. So here you can see where my diene was. It's got a CH3 and a methoxy group. This double bond right here is that bond right there, and it has everything hanging off of it that it normally did. No major stereochemistry to consider there. I do start getting into some stereochemistry with letter C. In letter C, my diene, these two are both either straight up and straight down. So when that happens, they over here need to be cis to one another. If one of them had been off to the side like this, more of like a axial equatorial type thing, then one of them would have needed to be a wedge. It would have been a trans situation. But everything else about the problem is fairly normal. With number 18, we are looking at a Diels-Alder reaction, and the idea here is to keep in mind that, well, for this thing right here is not symmetric. And when that's not symmetric, you should be asking yourself whether or not it's going to react the way it's drawn, or is it going to flip upside down and react more like this, where you have the COOCH3 down here. So you're asking yourself, which way is it going to add? What you want to keep in mind is that when you draw your cyclohexane, 1,2 addition is good, 1,4 addition is good, 1,3 addition is bad. Okay, so we want to avoid 1,3 addition. So let's go in and start drawing this thing. Here is my diene, and it's part of a ring. So I started with a cyclohexane that has this coming up right here. It has this extra carbon right there, so that is where I got this bridge right there. This bond came down to here, which is how I ended up with that double bond right there. At that point, this thing was a triple bond when one of those pairs of electrons is participating in the reaction, so that's going to drop down to a double bond. Now, we need to decide whether this thing right here was going to add where I have drawn it, or if it flipped upside down, it would add there. If it added, all right, so think of this is position 1, position 2, this would be position 3. If it were to add right there, that would be 1-3 addition. That's bad. So it needs to add right there to give you 1-4. So the idea is that you want 1-2 addition or 1-4 addition, but not 1-3 addition. In letter B, here's my diene. Once again, it is a cyclic one, so I've got my cyclohexane coming up like that with 2 extra carbons. That shows up here in my bridge with 2 extra carbons. Okay, this bond right here is this bond right here. Okay, and then the 1-2, 1-4 thing really doesn't come into play as much here because it's adding to this ring that you care about. So like you have this position right here, think of that as your 1. Something's adding here at 2 and here at 3, no matter what it is. So it really does not come into play in this particular example. So you could have drawn it this way, or you could have put the double bond down here, and you really kind of would have ended up with the same situation either way. It's both a 1-2 and a 1-3 addition. Letter C, in terms of my reaction, this bond's coming to here, coming to here, coming to here. So I'm going to have a cyclohexene. Okay, I'm going to go ahead and put my methyl group in place there, my methoxy group. And then this bond right here is that bond right there. So did this thing react the way it's drawn, or did it react like this? If this is position 1, this is position 2, here's position 3, here's position 4. I do not want this group to be right here. What I just drew is bad because that's 1-3 addition. I want it to be right here. You want 1-4 addition. So it really reacted more like this. It flipped. Let's do the same thing with letter D. This bond's coming to here, coming to here, coming to here. That's going to give me a cyclohexane. We're going to have a CH3 here, a CH3 here, and the double bond is there. This bond is this bond right here. So did it react that way, or did it react this way? Well, you got to start with something as part 1. I'm going to call this part 1, this part 2, part 3, carbon 2, carbon 3. So if I were to put my CN group right here, that'd be bad. We don't want to do that. But it's okay for it to be right here because that would be 1-2 addition. So the way I have it drawn, I have 1-2 addition. If we had started counting at the other methyl group, 1, 2, 3, 4, it would be 1-4 addition. Either way, you don't want it right here. Both of those groups would have given us 1-3 addition, and 1-3 addition is bad. Here in number 22, you're looking at the fact that conjugation affects your UV absorption. UV absorption will be the highest when you have the most conjugation. Now, I do admit that there are more numbers on the screen than there are potential questions down below. But what I looked at, I've highlighted all of the conjugated bonds. Those are highlighted for us. I see that letter A has 4 conjugated bonds. That's going to be, it's my most conjugated. I'm giving that one my highest number. Letter B and D both have 3 conjugated bonds, and then you'll notice that I placed B as a higher number above D. The reason for that has to do with substitution. Like this double bond is disubstituted, this one is trisubstituted, meaning the double bond has 1, 2, 3 carbon groups coming off of it, and then this one is trisubstituted. When I look at the ones over for part D, this one's tri, this one's di, and this one's di. So part B is a di-tri-tri, part D is a tri-di-di. More tris give this one a higher number. Okay? And then this one I gave my lowest number because it only had 2 of the conjugated bonds. In number 23, you've got phenolphthalein. Phenolphthalein is an acid-base indicator that is colorless at a pH of 8 and red above a pH of 8, and explain why one is colorless and one is not. So here's the one that's colorless. If you're following conjugation patterns, like I see conjugation here, which is conjugated within this ring, but then there's kind of a break in the conjugation. There's a little bit more conjugation down here, but it's separate from the conjugation up here. So there's 3 like separate areas of conjugation. That's an area of conjugation, that's an area of conjugation, and that's an area of conjugation. That one came out colorless. If we put this thing into basic conditions, So we're in basic conditions. It's going to take that hydrogen away right there. Okay, so the hydrogen that was right here is gone. That put a pair of electrons right here, and those electrons came down to here. So now I've got a double bond right here. Okay, check out your conjugation. Conjugated here, this is conjugated with this, conjugated with this, and then it goes down into the ring. This one's conjugated with this one, with this one, with this one. It's also like this bond right here is also conjugated with this bond and this bond and this bond, and then this bond is conjugated with that bond. The whole thing is conjugated. That's got a ton of conjugation in it. Increasing conjugation is what gives you your red color.